Hey guys, welcome back to chapter 17. In this video, I'm going to touch very quickly on buffer capacity. Your textbook does actually a pretty good job of explaining this. So I'm just going to touch on it so you hear it from my voice, but I suggest that you read up on this in the textbook more because it does a really good job. So buffer capacity, it talks about where the buffer is most effective. So there is a limit to how much of a strong acid or how much of a strong base you can add before the buffer becomes ineffective. So we add a little bit of strong acid, pH doesn't change much. We add a little bit of strong acid, pH doesn't change much. We add a lot of strong acid and all of a sudden, boom, that pH flies down. So there is a point where buffers are no longer effective. Okay. So the effectiveness of a buffer depends on two factors. So it depends on the amount of acid and base and the concentration of the acid and base. So when I say relative amounts of acid and base and concentration of acid and base, I'm talking about the acid and the base in the buffer. So weak acid and conjugate base, or weak base and conjugate acid. So that's what I'm referring to. Okay. So amount of acid and base and concentration of acid and base. Buffer capacity is the amount of acid or base that a buffer can neutralize. So up here, we're talking about, well, what makes a good buffer? And down here, we're saying, okay, that good buffer, how much can it really take on? Okay. And then buffering range, very much related to both of these, is the pH that buffer can be effective within, okay? So again, enough is enough when it comes to these buffers. There is a point where they don't work anymore. So a buffer is most effective when the concentrations of the buffer are high. So what we see in these two examples is here in our buffer, we've got a 0.5 molar concentration, 0.5 molar concentration. And here we've got a 0.05 molar concentration and a 0.05 molar concentration. So in these two solutions, the difference is we've got a higher concentration, lower concentration. We're going to add the same amount of strong base. And what we see is that the pH difference is pretty dramatic. So with the higher concentration, we see a smaller change. With the lower concentration, we see a bigger change. Okay, so most effective if the concentrations are high or higher. Here we see a buffer is more effective or most effective when the concentrations of acid and base are equal or closer to equal. So again, we're going to look at the same kind of example. So here we see 0.1 and 0.1. And here we see 0.18, 0.02. So we see a pretty dramatic difference in the concentrations, a high and a low. And here we see that they're the same. Again, we add the same amount of strong base. And then we test the pH. So here, the pH is changed by 0.09, so 5 to 5.09. Here we see the changes from 0.05 to 4.25. So this is like a 2% change, and this is like a 5% change. So when they're equal, small change. When they're not equal, we see a pretty big change here. So most effective when concentrations are high, most effective when concentrations are relatively equal. Next, we're going to talk about the buffering range. So a buffer will be effective when the ratio of the acid and base is 0.1 to 10. Kind of a weird way to state it. So you can verify this, so don't just take my word for it, but you can verify this through calculations. But if the buffer is effective between these ratios, essentially what that's saying is the buffer is effective plus or minus 1 of the pKa. So for example, the acetic acid buffer. Ooh, hey, dyslexia. The acetic acid buffer has a pKa of 4.74. So that means this buffer will be effective between a pH of +1, so 5.74, to -1, 3.74. So the buffer will be effective inside of that range. If I go outside of that range, so I affect the pH to a pH of 6, the buffer will no longer be effective. So that's what it's saying, is the pH of a buffer will be effective within that range. Another way that I can ask this, which I'm going to do on the very next slide, is I could say the pH of a solution is this. Pick the best buffer, okay? So let's just look at an example. So which of the following acids would be the best choice to combine with a salt to make a buffer with a pH of 4.25? So this is the pH of the buffer that we want, and we want to pick which one of these would be the best one to make the buffer out of. So if we want a pH of 4.25, it's certainly going to have to be within that range. So we're going to have to pick a buffer that's between 5.25 and 3.25. So something in this range, and then specifically the closest to that. So would we use this first one? No, because it's outside of our buffer range. It's way down here at the bottom, so that one would not be effective. Is nitrous acid within our buffer range? Well, yeah, it falls kind of right here. So it falls within the buffer range, so that's good. Is formic acid fall in our buffer range? Yeah, it does. It also falls in the buffer range, so probably about right there. What about hypochlorous acid? Is that within our buffer range? Nope, that's outside the range. So that would be ineffective. So we've got two that are within our range. So how do we pick the one that would be the best? Well, we want to pick the one that has the pKa that's the closest to the pH that we're dealing with. So in this case, 3.74 is closer to that 4.25. So the best buffer to use would be the formic acid buffer. So pKa is closest to the desired pH, and then also within the range, that would be the most effective buffer. So that's buffering, range, effectiveness, capacity. Like I said, your textbook has a lot more details on this, but I wanted to give you just a quick look at it. I hope you guys found this helpful.